go ahead and get started. This will be part 3 of the MRI Physics series that we've been doing. Again, drawn heavily from Prometheus's War Machine and the Einstein videos that are on YouTube. So if anything doesn't make sense, these are good references because they're basically what I'm taking my material from. So we'll start off with a couple slides of review. So hopefully this looks familiar to everyone who was watching the last 2 lectures. So we started out talking about how we generate some measurable signal in a patient. And if this is our MRI scanner, we talked about how a patient at rest out in the waiting room doesn't have any net magnetization. But if we slide them into the scanner in the presence of this external magnetic field, that what happens is all of the protons in their body align in one of 2 directions, parallel or anti-parallel, and that in the presence of this field there's a small net majority that align in the anti-parallel direction. We call that our net magnetization vector, or our m sub z, which is just magnetization in the z direction, the longitudinal direction. Basically, we get some net magnetization. And we said that, well, this is great, but we can't measure it directly because it's in the plane of this much, much larger field. There's no way we'd ever be able to detect the tiny vector that we've induced here. So we have to get it into the transverse plane. And so we said to do that, we're going to apply our RF pulse on the side here, in perpendicular direction to the resting magnetic field. And the other thing we're going to do is we're going to alternate this, or we're going to let it spin, this RF pulse, at some frequency. And if we match the frequency of our RF pulse to the frequency of the protons that are in the patient, then by the property of resonance, we'll get efficient energy transfer and we'll be able to move our vector up into this transverse plane. And then we decided that to exploit the difference between tissues and to start generating some contrast in our image, we're actually going to turn our RF pulse off. And we're going to watch the system decay back down to where it was initially up here. So what I've diagrammed out for you is basically just kind of the sequence of events. This is the patient just chilling in the scanner up at the top. We turn our RF pulse on here. And what happens to our vectors is diagrammed right here. And you see that as we turn our RF pulse on, our our longitudinal magnetization, our yellow arrow, goes from some magnitude to nothing. And that's diagrammed here. And we also see that whereas before we didn't have any transverse magnetization, which is our orangish red arrow, that grows. And that's diagrammed here. So every time we're turning on the RF pulse, this is happening, right? We're knocking our longitudinal magnetization down, and we're generating transverse magnetization. And remember that this transverse magnetization, this is the signal that we can actually measure directly. And then we said that we were going to turn the RF pulse off, right? We were going to let it return back down to this state right here. And when we do that, longitudinal is going to slowly recover, our yellow arrow, right? It's going to slowly regrow. And the transverse magnetization is going to decay. And it's going to decay quickly relative to the longitudinal regrowth. Okay, all of that should look pretty familiar from what we talked about last time. So when we do that, we essentially what we're doing right here by turning the RF pulse off is we're watching to see how quickly different tissues recover. Different tissues will return to that baseline state at different rates, both in their transverse vector and their longitudinal vector. And if we look at the difference between the rate at which they return to kind of their original resting state, that difference is our contrast. Okay, so this is again what we talked about last week. So this first curve is our T2 curve, right? The difference between water and muscle. So just to review, transverse magnetization decay, which is this curve, occurs via spin-spin interactions. Remember, those are interactions between protons, energy exchange between one proton and another. And we used water as the example of something that is moving freely. Those types of interactions are not particularly likely to occur just because the protons are kind of free to go wherever they want. They're less likely to bump into their neighbor. So that process of getting rid of energy takes longer, and that's why this curve is up here. It's a shallower curve. It takes longer to get to 37% of its original. And so it's got, its T2 is longer. We said that muscle, protons are, closer together. They're less free to move around. So they're more likely to bump into their neighboring protons and exchange energy. And that's why this curve, it's a faster decay. And their T2, the time at which they reach 37% of their original, is shorter. Okay. And it's this difference again, that's the difference that we're looking for between those two that allows us to decide if we want a tissue to have, to maximize the differences between, those, the way that those tissues release energy or not. And then, kind of a similar thing is going on in the longitudinal direction, right? This recovery back to, the original longitudinal magnetization is occurring via spin lattice interactions. So different than the spin-spin. Spin lattice interactions, we said, is energy exchange between protons and just other things in the sample. So kind of a similar idea here, the muscle, again, because it's a complex biological tissue. The protons in muscle are more likely to interact with other things in the lattice, and so they get rid of their energy faster and they return to that resting state faster. They have a shorter T1. Water is going to have a longer T1 because water is freely moving. It's less likely to release energy via those spin lattice mechanisms, and so its curve looks like this. Okay. Again, this is just all review from last week, but I want to be clear that everyone's on the same page. Okay. Okay. Last review slide. So we also talked about this last week. So this is illustrating where we get our signal contrast from. So the red box on the top here is indicating that this longitudinal magnetization is not directly measured. Okay, remember, this is not something that we can directly measure. If we go back a slide, this is not something we can directly measure, right? Because it's in the longitudinal direction. All we can directly measure is what's in the transverse direction. So we can measure kind of the difference between T2 directly, but not T1. So let's take this scenario over on the left first. I've showed basically what we just had on the previous slide, which is, our T2 curve, right? And this is basically pure T2. And the reason I say it's pure T2 is because it doesn't have any contribution from what's going on up here, okay? By the time that, this gets knocked down, we're starting from 100%. There's no difference between the muscle and the water here, okay? And so when you apply your RF pulse, and you knock this whole thing down to 0, and this goes up, it's going to go all the way up to the top, and it's just going to decay like we've been talking about. Okay, and then you measure your signal at some time to echo, some TE, and wherever you choose to do that, the difference in those curves is your contrast. Okay. Now, over on this side, this is more real. This is more of what we actually are getting in the wild here. We actually don't really acquire any images that are just pure T2 like this. Okay. Most of the images that we obtain are actually more like this. They have some degree of T2 contrast, and they have some degree of T1 contrast. So where are we getting the T1 contrast from? Remember we said that T2 contrast depends on time to echo, where you acquire your signal along this curve, right? If you acquire your signal at a longer time, if you allow more time for this decay to happen, you're going to have more contrast. And if you pick your time, your TE, to be shorter, you're going to have less contrast up here. So you can decide how much T2 weighting you want in your image based on what you set your TE. With T1 contrast, the way that we decide how much T1 weighting we want in our image is by adjusting our TR. Okay, and we said before last week, our TR is timed repetition. And time to repetition of what? Well, it's time to repetition of our RF pulse. So remember, we have like an RF pulse that's right here, kind of along, the y-axis itself. That's knocked this transverse magnetization down to 0 in the first place. And then we turn the RF pulse off when we watch it recover. And then before it's recovered all the way, like over here, we knock it down again. Okay. And when we knock it down again, there's some difference between where our muscle curve and our water curve are at. Okay, muscle is going to have recovered more, so its magnetization in the longitudinal plane is going to be more than water. And so when you knock it down, you're going to have more signal in muscle because you had more to begin with when you applied your RF pulse and you put this magnetization in the transverse plane. Again, it's just this happening over and over again. And if this is bigger to start with, you're going to have more here when you apply your RF pulse. If this is bigger to start with, you're going to have more here after you turn your RF pulse on. That's all that we're saying right here. This is bigger to start with in muscle. And so when you apply your RF pulse, you're going to have more transverse magnetization. Okay, and it's that difference here that actually gets kind of encoded in the start positions here, in the transverse magnetization curves. And so practically speaking, what happens here is that the curves as you go over time are going to look different than if you had given everything enough time to fully recover here. These curves look different, even though the TE is the same. You're measuring at the same time, but what we've done here is we've adjusted the TR. Okay? And so this image is actually a combination of the differences in T2 decay between the tissues, and it's a combination of the differences in the T1. Okay, so this curve is actually a combination of this information and this information. And like I said before, this is kind of more what we get in the wild. And we just adjust how much of this we want and how much of this we want, right? How much T1 weighting and how much T2 weighting by adjusting TR and TE. Okay, so up to this point, lecture 1, we kind of talked about magnetic resonance and what it is, how we get any signal at all that's measurable. Lecture 2 was talking about contrast, right? Differences in the way that these tissues are giving off energy after we apply our RF pulse. And we watch those curves that we just talked about, and those differences in the way that, in the rate at which those curves return to baseline, gives us contrast. Okay, when we acquire a signal, we can tell the difference between fat and water, muscle and water. So we talked about magnetic resonance and generating signal. We talked about contrast. Now we need to talk about spatial resolution. Well, how do we tell where that signal is coming from? And this is where we start getting a little bit into the weeds with MRI. So I'm going to go slow. and try to make this actually make sense. Um, but I don't want to rush through this because this is, I think, the most confusing part for anyone who's ever looked at or studied MR. So we're going to start really basic. Okay, we're going to be talking a lot about gradients, so it's important that we're all on the same page. When I say a gradient, I mean a gradient. We all know what a gradient is, right? It's this. It's something that is changing um, over some distance, right? So, this is a blue gradient. This gradient we can represent with a graph. Okay. Why do we care? So, kind of like I alluded to before, gradients are going to be the basis for localizing our signal in space. We generated a signal. We know how we can tweak TR and TE to weight our image more to T1 or T2 or um, proton density even, like we talked about last week. But now we need to figure out where it's coming from. Okay. So this is an illustration of gradient magnetic fields, and what we have here at the top is our patient in the scanner, kind of resting state. And this is everything that we've set up before with our resting state, with our external static magnetic field, or 1.5 Tesla field, or a 3 Tesla field, whatever type of scanner it is. And remember that this field is homogeneous, right? It's not changing. It should be nice and uniform throughout the entire scanner. Okay, so it's B sub 0 by the feet, and it's B sub 0 by the head. Okay. And the way that we actually generate this field is there's like these coils, okay, that wrap around the whole bore of the scanner like this. And they run lots and lots of power through these, okay, to generate or to induce a magnetic field. Okay. So that's kind of the concept of what's happening here. That's how they're generating this B naught field in the first place. Okay. And if we were to graph this field, kind of like that gradient, right? All we're doing is this. If we wanted to graph what this field is doing, from one end of the patient to the other, our graph would look like this, right? It's just uniform, homogeneous. The field's not changing even as we move in the z direction here, right? The longitudinal direction. This is field strength. This is moving from the patient's feet to the patient's head. It's not changing. Okay. This is baseline when the patient slides into the scanner. Now, what I've diagrammed down here is the application of a gradient magnetic field. Gradient magnetic field is basically where you have coils that are placed, at different points around the patient. In this case, we've placed them, down by the feet and up by the head. And these gradient coils are going to induce additional magnetic fields. And this is not fixed. We can change these gradient magnetic fields to be whatever direction we want. In this case, I've chosen to align them in a anti-parallel direction and a parallel direction with respect to, that resting magnetic field that we had to start with up here, right? So if our resting magnetic field is going this way, one of those gradient coils will create a field that is going opposite it, and one of those gradient coils will create a field that's going with it. So what happens to the net magnetization, okay, that's experienced by the protons in the patient? Up by the head, it's going to be a greater net magnetic field, right? Because these are both going in the same direction. And so it's actually the sum up here of whatever we had to start with plus this additional field that we've added. Okay, B naught plus, our gradient magnetic field. Down here by the feet, it's, the opposite is true. Okay, we have applied a gradient coil, generated a magnetic field that is opposing, our initial magnetic field. And so the net magnetic field down by the feet is going to be weaker. Okay, so it's going to look like this instead of a nice straight, uniform line. And if we were to graph what's going on here with our net magnetic field kind of being graphed on the side here, and as we move in the longitudinal plane from the patient's feet to the patient's head, what's happening is that down by the feet, our net field is at, or our net magnetic field strength is actually, down here. It's lower. And up by the head, it's higher. Okay. So by applying a gradient magnetic field, or these gradient coils, we're able to generate a gradient in our magnetic field. We're able to go from a situation where we had a nice uniform single magnetic field strength throughout the entire patient to a situation where now that field is changing in a predictable manner as we move, from the patient's feet to the patient's head. This is what a gradient magnetic field is. I've sort of re-diagrammed our last slide right here. And the point that I'm making here is that just as when we apply those gradient coils, that gradient magnetic field, we induce a gradient across our magnetic field, across our patient, which is here. The other thing that's happening is that just as the magnetic field strength is changing from the patient's feet to the patient's head like this, the other thing that's changing is the frequency of the spins, right? Remember, this is our Larmor equation, which we said, the takeaway from that was that, your field strength is proportional to your frequency. Okay. If your net field strength is higher up by the head, the frequency of those spins is going to be higher too. Okay. If your net magnetization down by the feet is lower because of this gradient that you've applied, well, it's not just the magnetic field strength, the frequency of the spins is also going to be slower. Okay, and this is just that relationship that we established in the first lecture, the Larmor equation again. Okay, magnetic field strength is proportional to the Larmor frequency, okay, to the rate at which the protons are spinning. Protons are going to spin faster up by the head, slower down by the feet, because you've induced this gradient magnetic field across the patient. Now, these gradients can be created along any axis. So I've diagrammed this, up until now as kind of like just in this one direction. But realistically, you can take those coils and you can put them, kind of in any orientation you want. Okay, so it's not just one gradient. We actually use a lot of different gradients with MRI. And so you can induce changes across the patient in your magnetic field and in your frequency by applying these gradients in different directions. Okay, so our initial one, we showed what happens if we apply it in the blue direction and the longitudinal direction, right, by having our coils here and here. If we wanted to apply it in the y-axis, right, we might have a coil up here, a coil down here, and the field would get stronger as you go to the top, or we could reverse it. You can kind of flip these things around. So the takeaway here is just the gradients can be created along different axes, but for simplicity's sake, we're going to keep everything in the same plane. So we can create a gradient across the patient. We can create it in any axis we want. We can also change how strong we want the gradient to be. Okay. So like I said before, remember, when we create our B naught magnetic field, it's, we're running power through coils, and that induces the magnetic field. The same is true with these gradient coils. Okay, we're running power into these gradient coils to generate these gradient fields. And if you use less power, or some amount of power here going through those coils, you might generate a gradient that looks like this, kind of a gentle change from the feet to the head. If you ramp up the power, you have a bigger gradient in this direction and a bigger gradient in this direction. Well, as you would expect, you're going to be more negative down by the feet, and you're going to have more positive net magnetization up by the head. Okay, and as a result, when we plot this, on this graph here, again, z-axis here, and just strength of our net magnetization, our net magnetic field strength, or our frequency, right? that this is going to be a steeper slope than this. Okay. We're going to have a steeper gradient, a stronger gradient, a larger gradient, all ways of saying the same thing. And the way we do that is just by ramping up the power, giving it more juice. Okay. So gradients can be weak or strong. We decide how strong we want our gradient to be, how much change we want to induce across the patient by how much juice we give the gradient coils. Okay. So we started talking about gradients, but why do we care about gradients? Remember, gradients are the basis for localizing our signal in space. So this is where we kind of start our real discussion. This is what we have so far. Okay, this is our patient in our scanner. We have our uniform homogeneous magnetic field. We haven't applied any gradients yet. And in this patient, because the field is uniform and homogeneous throughout the patient, the spins are all the same, right? All the protons are spinning at this, Larmor frequency. And as we said before, when in this uniform field, everything's spinning with the same frequency, and when we apply our RF pulse at the same frequency, we're going to excite those spins, right? We're going to excite those protons. If everything here is processing at a frequency of 5, okay, and we apply our RF pulse with a frequency of 5, we're going to excite all those protons. Here's the problem. The signal is coming from the whole patient. Okay. When you sample signal, I'm going to skip ahead just briefly. When you sample the signal from this patient, it looks like this. Okay. And actually, if you sample the signal from the whole patient, it's going to look like an extraordinarily messy version of this. Okay. So you have no idea at this point how to tell where signal is coming from. It's not like, oh, you have a little receiver here and a little receiver here and a little receiver here, and this little receiver can separate the signal that's coming from this side, and this little receiver can separate the signal that's coming from here. No. Okay. You're collecting signal from the whole thing at the same time. Okay. So the signal you get is purely a function of what have you excited. So with this system that we've set up right now, without any gradient, when we turn on our RF pulse, we're exciting all the protons in the patient. We're generating our transverse magnetization, but what we get is going to be something like this. This is where we're at right now, okay? We have basically our image is a single voxel, okay? We have generated signal from the whole patient, and our image is going to look like this, which is not super useful. The next thing that we're going to do is we're going to move to a place where we're only exciting a slice at a time instead of the whole patient. Okay, eventually we'll move to this. Probably not today. That'll be next time. But getting down to the level of having individual, voxels, pixels in an image. And that's kind of the third and final step. So this is where we're at. We're exciting everything. How do we just get to the point where we're exciting just a slice? Well, I introduced the concept of gradients for a reason. And so this is the reason. So when you apply a gradient, I'm just going to reiterate what we said before. When you apply a gradient, the field strength and the spin frequency are going to vary across the gradient, right? Field strength is going to be less down here. Spins are going to be slower down here by the feet. As you move across the gradient, spins are going to be moving faster up by the head, and the net magnetic field strength is going to be stronger up by the head, okay? So now check this out. With this sort of situation, it's still the same deal. Because of resonance, the only spins in the body that are going to be excited are the ones that have the same frequency as our RF pulse, right? So before here, we said that if we set our RF pulse to a frequency of 5, and all the spins in the body are spinning at 5, we're going to excite everything in the body. Let's say our RF pulse is still, we have it set to 5, it's still 5 here in the center, kind of where, this is getting more negative, this is getting more positive, but here it's still kind of B naught where we started at. These spins are going to be spinning at 5 right here, but these are going to be like, 4, 3, 2, 1, 0. As you go in this direction, it's going to be like, 6, 7, 8, 9, 10, 11, as you go towards the head. Okay, so by applying that gradient, now instead of having all the spins in the body spinning at the same frequency, only some of them are spinning at the frequency at any given frequency, right? And so depending on what you set your RF pulse frequency to, if you set it to 7, you'll select a slice up here. If you set it to, 3, you'll select a slice down here. If you set it to 5, you'll select this slice. Right? Because again, it's that idea of resonance. You're not going to excite everything. You're going to excite only the stuff that's spinning at the same frequency. So this is the setup where, now we can select an individual slice. Take this idea of slice selection, and we're going to look at it from a number of different angles, because I think that's kind of what you have to do with this stuff to understand it. And this is in Prometheus's book, so it's a good reference for this stuff at least. So again, this is the same thing that we have diagrammed here, right? I haven't changed anything. All I've done is I've graphed the gradient down here. On our y-axis, we have our frequency. How fast are these things spinning? And we said that this was proportional to the field strength, right? So we've created a gradient of magnetic field, but it's also a gradient of frequency because those things are proportional. And, as you go from the patient's feet here, this is our z-axis again. As you go from the patient's feet here to the patient's head, things are moving faster. You have a gradient. So if we, and I'm picking just arbitrary numbers again here, if we say that at, without the gradient, everything would be at, frequency 0. Without the gradient, everything would be at 0. Okay, but with the gradient now, we're only going to apply our RF pulse with a frequency between -1 and +1. Okay, RF pulse is not like one single number. So essentially what we're saying here is we're going to excite all the spins that are spinning at a rate of -1 to +1. So if we look, what spins are we exciting? Well, okay, so we look on our y-axis, and this is how fast they're spinning. And okay, so -1 is here and +1 is here. So if we look at kind of what we're catching, which is this red bar here, it's this. Okay, these are going to be the spins that have, that are spinning with a frequency of -1 to +1. These spins over here are higher, these spins are lower. So where does that match up on the patient? Well, okay, so it's this slice. This is the basis for our slice selection. And this range that we're picking is called transmit bandwidth. Okay, it's the range that you're transmitting your RF pulse at. Transmit bandwidth basically just says, it's the range of frequencies that you're trying to excite in the patient. We've established a gradient. We've applied our RF pulse across some range of frequencies. And by doing so, whatever range of frequencies we apply our RF pulse across is going to be the range of frequencies that we excite in the patient. And all that we're saying here is that if we say we're going to apply RF between -1 and +1, we're going to excite only the spins in this patient that are between -1 and +1. And if we graphed that, it would look like this. Only these spins right here in the middle are going to be between -1 and +1. If we change this to be, I think I may have it on the next slide. Yeah, if we change this, if we change our transmit bandwidth, instead of -1 +1 to -6 -4, we're going to select a slice down by the feet. Okay, because now we're selecting spins that are down here. Okay. This is like -4, this is -6. Transmit bandwidth, if I say transmit bandwidth, like all that's saying is, what range of frequencies are we exciting? What range of frequencies are we actually going to get signal from? Because remember now, we're not getting signal from the rest of the body because we don't have that efficient energy transfer, right? These guys are not spinning at the same frequency as our RF pulse. So they're just not excited. We don't generate any transverse magnetization from the guys here, from the guys here. It's only the ones, in that narrow range in our slice. So a couple more things about this. So how can we manipulate this? We don't acquire all slices are not created equal, right? So what happens if we compare using a small transmit bandwidth or a narrow transmit bandwidth to a large transmit bandwidth? So same scenario going on here. The only thing that's changed between these two setups is the transmit bandwidth. Here, this is what we talked about before, where, we're going to apply our RF pulse at frequencies between -1 and +1. And, that was this here. So in this range of frequencies, which means that in the patient, that range of frequencies is only going to be found in the middle. We're going to acquire this slice. Okay. In this setup over here, we've adjusted our transmit bandwidth and we've made it wider. Okay, we've increased the transmit bandwidth, we've widened it. It's a larger transmit bandwidth, however you want to say it. But the long and short of it is that our transmit bandwidth is now -3 to +3. We're applying our RF pulse between these frequencies over across a greater range of frequencies. What does that look like on our graph? Well, basically you're saying that, okay, well, I'm gonna excite everything between -3 and +3. Well, that should be pretty intuitive. You're exciting a greater range of frequencies, which means you're going to be exciting more spins in the patient across a greater range, so your slice is going to be a lot thicker. If you increase your transmit bandwidth, if you apply your RF pulse across a narrower range of frequencies, you're going to have thinner slices. If you apply your RF pulse across a greater range of frequencies, if your transmit bandwidth is larger, you're going to have thicker slices. So, small transmit bandwidth, thinner slices. Larger transmit bandwidth, thicker slices. Okay, here's the other thing that we can do. So, we can also change the strength of our gradient. Remember how before I said that we can change the strength of these gradients based on how much juice we run through the gradient coils, right? So here we have a situation where we have a smaller amount of juice being run, a smaller or shallower gradient, and over here we have a larger amount of juice, right? Our battery is bigger. And so our gradient coils and our gradient magnetic fields are stronger. And so the overall gradient that's created across this patient is stronger, or it's steeper, right? You have a greater amount of change from one side to the next. In this case, it's, let's say -10 at the feet and +10 at the head. Here, it might be -15 at the feet, +15 at the head, okay? Because we've run more juice through our gradient coils. Same transmit bandwidth, everything else is the same, but we've increased the strength of our gradient magnetic field. So what happens is that because you have a greater amount of change across the patient, and so if we're still going from -3 to +3, well, that's going to be occurring over a shorter distance, okay? Because the distance of the patient has not changed. It's -10 here and it's +10 here. The frequencies, right? Their frequency might be -10 here, +10 here, 0 in the middle. If we really ramp up our gradient, I mean, we could make it -100 down here and +100 up here if we wanted to, okay? The length of the patient obviously is not changing, but our gradient is becoming much, much, much stronger. And because it's getting much, much stronger, you're covering more distance, or you're covering a greater range of frequencies in a smaller distance, okay? And so our slice is smaller than it was over here. Everything else is the same about these. The only thing that's changed is the slope of the gradient. How strong is our gradient? Here we have a stronger gradient, and so our slice is smaller. Here we have a weaker gradient, and so our slice is thicker. Weaker gradient, thicker slice, stronger gradient, smaller slice. Because this is occurring over a shorter distance. Okay, so this is sort of summarizing what we just talked about. So we talked about selecting slice location and thickness of our slices. So slice selection, our slice selection gradient, which was those yellow coils, that gradient that we induced across the patient. Slice selection gradient allows us to match our frequency to the slice of interest. And that's, this right here. And depending on where we set our RF frequency, we can choose what slice we want. So all of this is the slice selection gradient. Okay. Which, we call it a slice selection gradient because it allows us to select our slices. So we talked about slice selection gradient and how we pick our slice by selecting our RF frequency. We talked about how to make thinner slices, and we can do that in two different ways, right? We can use a narrower transmit bandwidth compared to a larger transmit bandwidth here. Excuse me. This is a narrower transmit bandwidth. This is a thicker transmit bandwidth. Same gradient strength, same slope of the gradient. This is just a narrower bandwidth, and here it's larger. This is between -1 and +1. This is between -3 and +3. So thinner slices with a thinner transmit bandwidth. Thicker slices with a larger transmit bandwidth. The other way we can get thinner slices is with a stronger gradient, right? So, between here and here, strong gradient, weaker gradient, same transmit bandwidth, -3 to +3 in both cases. But because we're covering more ground with this gradient, our slice is smaller. There's just a greater rate of change of frequencies across the patient, and so the slice is smaller. Here, it's thicker. Okay. So this is just kind of like the core takeaways from slice selection and how you get a thicker or a thinner slice and how you pick your slice. Any questions about this? This is just summing up what we just talked about. Okay, so we went from exciting the entire patient and getting signal from everything, right? To now we've applied a slice selection gradient here. We're only exciting spins that match our RF frequency. And depending on where we set the transmit bandwidth of our RF pulse, we can acquire a slice through the head or through the feet or, wherever we want. So this is what we've got to now. The next part, which I'm not going to get into today, because we're already kind of at almost 8:30 here, is cutting this further into pieces to actually get our individual pixels. So taking our slice and creating voxels with it, or 3D pixels. Okay. The way we're going to do this, and I'll just, spoil it now, is we're going to apply more gradients. Okay. Just kind of like we used a gradient to cut this into smaller pieces here, we're going to use 2 more gradients to take our slice and cut it into this. Okay. Which sounds straightforward, and I think that's the problem, is there's some fuckery that happens, and I want to be able to take the time to explain what's going on, because I think that's where most of the misconceptions arise, is with this step, and this is the phase encoding and frequency encoding step. So that'll be next time. The last thing I want to touch on here, we're just going to introduce this idea of free induction decay. And I say introduce, but this is nothing new. Okay, this is exactly what we've talked about before. Okay, so don't freak out. This is our signal that we're acquiring. Remember, this is our transverse magnetization on the y-axis, and this is over time. Okay, so this is actually going to look like, let's find it here. Yeah, it's going to look kind of like this, right? This was our phase diagram before. So it's the same deal. So this is how much signal we have. This is our transverse magnetization in the transverse plane. And this is where we've applied our RF pulse here. And then we watch it decay over time. Okay. So as the actual signal kind of oscillates back and forth, it creates this decay curve. And we said that was, our T2, right? That represented our T2 curve. And if you'll recall at the end of last lecture, I introduced the idea of T2 versus T2 star. And basically, it's the same thing that's happening. T2 is just kind of like an idealized, where we have a perfect external magnetic field. And there's no inhomogeneities, there's no irregularities in the field. This is what we would expect to happen. And we said that, well, in the real world, this is what happens, this red arrow. And that's due to kind of local field inhomogeneities. Okay. So if we just measure the signal that's coming from the patient or from the slice that we just excited, it might look something like this, slowly decaying over time after we turn our RF pulse off. And remember, what's happening is that all the spins are slowly dephasing over time until they're completely dephased and we have no more magnetization in the transverse plane. Generally speaking, we don't want to see the effect of all of the little field inhomogeneities, all of the little ferromagnetic, particles and stuff that that are in the body, and so this signal is going to be, more prone to artifact. It's going to be dirtier. It's going to have a lower signal to noise ratio. All the bad things. So there's a way that we can get back to sort of the idealized T2. And the way we do that is with the generation of a spin echo, which is what this is here. So this is what we just showed. This is sort of what happens. We apply our RF pulse here, and I say 90 because we're covering 90 degrees. We're going from our longitudinal magnetization to our transverse magnetization. Okay, so the angle of change is 90 degrees, otherwise known as the flip angle. Okay. This is what we've been doing the whole time. Everything we've been talking about is assumed a 90-degree flip angle. Okay. So it turns out that we apply our RF pulse along with our slice selection gradient, right? So we're only selecting a single slice. And we start to, watch our signal, and our signal is decaying over time, and it's decaying over time, and these guys are dephasing. At some point, what you can actually do is you can apply another RF pulse, this time 180 degrees. So what's happening is you're flipping things from kind of this orientation all the way down to this orientation. Okay. This is everything we talked about. And then at some point you apply an RF pulse, 180 RF pulse, and it flips all of your spins over. And so now instead of diverging, they start to come together again. So the signal starts to reform because now things are going back into phase. It's not going to reform to the same degree as you had before, but it starts to regenerate. And then at some point it'll start to decay again, okay, as they start to get out of phase. Now, why do we do this? Well, initially, the decay curve, if we plotted our signal, looked like this. And that was our T2 star, we said, with all of those inhomogeneities, all of those artifacts. It's coming down faster, right? Because it's losing signal quicker, or it's losing energy quicker because of all of those artifacts, all of those inhomogeneities. It's dephasing faster. So this is our T2 star. When we flip this, with a 180 pulse and we kind of regenerate signal, the signal that we're regenerating is a much cleaner signal and actually doesn't have the information of all of those artifacts in it. So when we measure our signal, if we want to measure more of our ideal T2, we measure it out here. We measure it during our echo, okay? Because this curve, as the echo decays, is our idealized T2 curve. That's why we That's why we use an echo. That's the whole idea of the spin echo. There will be sequences where we don't do this, and we just look at the T2 star. It's our gradient echo sequences. So there are actually sequences that will acquire without doing that 180 degree additional RF pulse, and we just look at the T2 star. Those are the gradient sequences that we get, the GRE. Okay. But for the majority of the sequences that we get, we apply this additional RF pulse at 180 degrees. And what that does is two things. It reconstitutes the signal, and it puts these guys kind of progressively back in phase. Okay, and then that'll start to decay again. But this time when it starts to decay, compared to initially, it decays along kind of our idealized T2 curve. So if we wanted to acquire an image that's minimizing the amount of artifact, we're going to acquire it in this range. Okay, so next time we're going to talk about, we're going to kind of put everything together. We're going to make our phase diagrams. We're going to talk about frequency and phase encoding.